Preparing for a software engineering at Dynatrace interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a highly scalable telemetry ingestion service? I would place stateless ingestion nodes behind a load balancer and accept metrics, logs, and traces through authenticated APIs. A partitioned streaming layer would absorb bursts, while consumers batch, compress, validate, and store data in scalable backends. Partition keys should preserve tenant locality without creating hot partitions. I would add quotas, backpressure, retries with limits, dead letter handling, and end-to-end metrics. The design prioritizes availability, but retention and durability policies control storage cost. While answering, cover ingestion protocols, stateless service instances, partitioning, buffering, backpressure, horizontal scaling, tenant isolation, schema evolution, durability, observability, and graceful degradation during traffic spikes. Question 2. What is the difference between metrics, logs, and distributed traces, and when would you use each? Metrics are compact numerical time series used for trends, alerting, and capacity planning. Logs are timestamped event records that preserve detailed context, making them useful for auditing or debugging specific failures. Traces follow a request across services and expose latency, dependencies, and error propagation. I use metrics to detect a problem, traces to localize it, and logs to explain it. Correlation IDs and consistent resource attributes connect all three signals. Make sure to cover data structure, cardinality, diagnostic purpose, correlation identifiers, storage costs, aggregation, sampling, and how combining signals accelerates root cause analysis in production systems. Question 3. How would you implement a thread-safe cache in Java? For a basic cache, I would use concurrent hash map and store values with expiration metadata. The get operation checks freshness, while compute if absent can prevent duplicate loading for the same key. However, expiration and eviction still need careful coordination, especially under concurrent access. I would bound capacity using an established cache library rather than hand-building complex policies. I would also define stale read behavior explicitly, because thread safety does not guarantee data freshness. In your answer, discuss concurrency primitives, concurrent hash map, atomic loading, expiration, eviction, cache stampedes, memory visibility, stale data, bounded capacity, and why correctness must precede optimization. Question 4. Explain how garbage collection affects the performance of a Java microservice. Garbage collection reclaims unreachable objects, but frequent allocation can increase CPU usage and pauses. Young generation collections are usually short, old generation collections can create longer latency interruptions depending on the collector and heap state. I would inspect allocation rate, pause distributions, live set size, and out-of-memory events rather than tuning blindly. Reducing temporary objects, right-sizing the heap, and selecting a collector for the latency target usually matters more than arbitrary JVM flags. Be sure to mention heap generations, allocation rate, pause times, collector selection, latency versus throughput, memory leaks, object churn, profiling, container limits, and validating changes with production-like workloads. Question 5. How would you troubleshoot a production latency increase using observability data? I would first confirm the increase through latency percentiles, not averages, and identify affected endpoints, regions, tenants, and versions. Distributed traces can reveal whether time moved into application code, queues, databases, or external dependencies. I would correlate the change with deployments, traffic, resource saturation, and error rates. After forming a hypothesis, I would test it with a targeted rollback, query, or controlled comparison, then add an alert or dashboard to prevent recurrence. Focus on establishing a baseline, checking service-level indicators, comparing deployments, tracing critical paths, examining saturation and dependencies, narrowing scope, validating hypotheses, and documenting remediation and prevention. Question 6. Design a distributed rate limiter for a multi-tenant SaaS platform. I would use a token bucket limiter, assigning each tenant a refill rate and burst capacity. A shared low-latency store or collocated partition would perform atomic token updates, preventing concurrent requests from exceeding limits. Keys should include tenant, API, and possibly region. If the store is unavailable, the policy must choose controlled fail-open or fail-closed behavior based on endpoint risk. Responses should include retry guidance, while dashboards expose rejected requests and quota consumption. Cover token bucket or leaky bucket algorithms, tenant-specific quotas, atomicity, distributed state, clock issues, fail-open versus fail-closed behavior, burst handling, response semantics, and operational visibility. Question 7. What makes an API reliable and maintainable in a large engineering organization? A maintainable API has an explicit, versioned contract with stable semantics and predictable errors. I would validate inputs, enforce authentication and authorization, use pagination for collections, and make write operations idempotent where retries are possible. Timeouts, rate limits, request identifiers, and structured logs improve reliability and supportability. Backward compatibility should be tested in C, and deprecation should include timelines and migration guidance rather than silently changing behavior. In your answer, cover explicit contracts, versioning, idempotency, pagination, validation, authentication, authorization, consistent errors, timeouts, rate limits, documentation, compatibility testing, and observability. Question 8. How would you design a reliable alerting system that avoids alert fatigue? I would alert primarily on user-impacting symptoms, such as an SLO burn rate, rather than every low-level fluctuation. Multi-window thresholds can detect both fast outages and slow degradation. Alerts should include ownership, severity, affected entities, evidence, and actionable runbooks. Grouping related events prevents storms, while dependency-aware suppression reduces duplicate notifications. I would review false positives, missed incidents, and time to acknowledge regularly, treating alert quality as an engineering metric. Discuss symptom-based alerts, service-level objectives, thresholds, anomaly detection, aggregation, deduplication, dependency awareness, severity, routing, evaluation windows, ownership, and measuring false positives and missed incidents. Question 9. Explain eventual consistency and describe when it is acceptable. Eventual consistency means replicas may temporarily disagree but converge if updates stop. It is appropriate when small delays do not harm correctness, such as aggregated dashboards, usage analytics, or search indexes. I would avoid it for authorization decisions, financial balances, or workflows requiring immediate read after write behavior. The design should state acceptable staleness, expose synchronization status when useful, and handle conflicts through versioning, ordering, or deterministic merge rules. Make sure to explain delayed replica convergence, read your writes expectations, conflict handling, user impact, strong consistency alternatives, and examples such as analytics, dashboards, and configuration management. Question 10. How would you prevent duplicate processing in an event-driven system? I assume delivery is at least once, so consumers must be idempotent. Each event gets a stable identifier, and the consumer records processed IDs alongside the resulting state when possible, using one atomic transaction. For external side effects, I would use idempotency keys or an outbox-based workflow. Acknowledge messages only after durable processing, retry transient failures, and isolate poison messages. Exactly once behavior is usually an end-to-end effect, not merely a broker feature. Cover at least once delivery, idempotent consumers, event identifiers, deduplication storage, transactional boundaries, acknowledgement timing, retries, poison messages, and why exactly once claims require careful qualification. Question 11. What testing strategy would you use for a distributed observability platform? I would use unit tests for parsing, aggregation, and business rules, then integration tests for databases, queues, and protocol boundaries. Contract tests protect compatibility between agents, ingestion services, and storage components. Load tests should model realistic cardinality and burst patterns, while fault injection validates retries, outages, and partial failure. End-to-end tests cover critical user journeys. I would keep tests deterministic, publish performance budgets, and use production incidents to expand coverage. Discuss unit, integration, contract, property-based, load, failure injection, end-to-end, security, and compatibility testing, plus deterministic fixtures, test data, performance budgets, and production feedback. Question 12. How do you investigate a memory leak in a long-running Java service? I would verify whether memory growth is heap, direct buffer, thread, or native memory, because each requires different tools. For heap growth, I would capture dumps over time, compare retained objects, and inspect dominator trees and reference paths. Common causes include unbounded caches, static collections, forgotten listeners, and thread local state. After identifying the retention path, I would reproduce the issue, apply a targeted fix, and run a long soak test before deployment. Focus on reproducing growth, distinguishing heap from native memory, comparing heap dumps, inspecting dominator trees, identifying retention paths, reviewing caches and listeners, and confirming the fix through soak testing. Question 13. How would you handle high-cardinality telemetry without making the system too expensive? High-cardinality improves diagnosis but can multiply ingestion, indexing, and query costs. I would measure cardinality by attribute and tenant, separate dimensions needed for alerts from those needed only during investigation, and apply quotas or allo lists. Aggregation and tail-based sampling can reduce volume while retaining unusual errors or slow traces. I would use tiered retention and avoid indexing every field. The goal is controlled detail, not blindly maximizing data collection. In your answer, cover cardinality measurement, aggregation, indexing strategy, attribute allo lists, tenant quotas, retention tiers, sampling, exemplars, query performance, and preserving diagnostic value. Question 14. Describe a robust deployment strategy for a critical backend service. I would build an immutable artifact, run unit, integration, security, and migration checks, then deploy gradually through a canary. Health checks should test meaningful dependencies without causing cascading load. I would monitor error rate, latency, saturation, and business-level indicators against the previous version. Database changes must remain backward compatible during rollout. Feature flags separate deployment from activation, and automated rollback should trigger on predefined thresholds with a documented recovery path. Be sure to mention immutable artifacts, automated validation, backward compatible migrations, canaries, health checks, rollout metrics, rollback triggers, feature flags, capacity planning, and database compatibility. Question 15. How would you secure an agent that collects data from customer environments? I would run the agent with the minimum operating system permissions and collect only approved data. Mutual TLS, short-lived credentials, secure secret storage, and regular rotation protect communication. Updates should be signed and verified before installation, with rollback support. Data must be encrypted in transit and at rest, and tenant boundaries enforced server-side. The agent should buffer safely during control plane outages, expose audit events, and avoid making sensitive content available in logs. Discuss least privilege, mutual authentication, encrypted transport, secret rotation, signed updates, data minimization, tenant isolation, local buffering, tamper resistance, auditability, and handling unavailable control planes. Question 16. What is the N+1 query problem, and how would you diagnose and fix it? N+1 occurs when one query loads parent records and then one additional query runs for each parent. I would detect it through SQL logs, query count assertions, database traces, or endpoint latency analysis. Depending on access patterns, I might use a join fetch, batch loading, a dedicated query, or a data loader pattern. I would avoid blindly eager loading everything, because that can create large results and memory pressure. Benchmarking with realistic cardinality confirms the fix. Cover repeated child queries, ORM behavior, query counting, tracing, eager versus lazy loading, joins, batching, pagination, memory trade-offs, and verifying improvements with realistic data volumes. Question 17. How would you design a resilient service when a downstream dependency becomes slow or unavailable? I would set deadlines that fit the caller's latency budget and cap connection pools so one dependency cannot exhaust all threads. A circuit breaker can stop repeated calls during failure, while bounded retries with exponential backoff and jitter address transient errors. Bulkheads isolate workloads, and graceful fallbacks or cached results preserve partial functionality. I would shed non-essential work when saturated and monitor dependency latency, rejection, breaker state, and user impact. Focus on bounded timeouts, connection pools, circuit breakers, bulkheads, retries with jitter, fallback semantics, queuing, load shedding, dependency budgets, and distinguishing transient from permanent failures. Question 18. Which data structures and algorithms would you expect to use in a software engineering coding interview? I expect problems involving arrays, strings, hash maps, stacks, queues, trees, graphs, heaps, sorting, binary search, and occasionally dynamic programming. I first clarify constraints, state a straightforward approach, then improve it while explaining time and space complexity. I test empty inputs, duplicates, boundaries, and large values before polishing code. For example, a hash map often changes a pair sum search from quadratic time to linear time, at the cost of extra memory. Mention arrays, hash maps, stacks, queues, trees, graphs, heaps, sorting, binary search, recursion, dynamic programming, complexity analysis, edge cases, and communicating trade-offs before coding. Question 19. Tell me about a time you improved reliability or performance in a production system. In one service, P99 latency rose during traffic bursts because synchronous enrichment consumed worker threads. I used traces and thread pool metrics to isolate the dependency, then moved enrichment behind a bounded queue and cached stable metadata. We added deadlines, fallback behavior, and alerts for queue depth. A canary showed lower P99 latency and no unacceptable staleness before full rollout. The lasting improvement was a load test representing burst traffic, not just average throughput. Make sure to structure the response with situation, measurable impact, investigation, technical decision, collaboration, validation, rollout, and the lasting prevention or monitoring improvement. Question 20. Why do you want to work at Dynatrace, and how would you contribute as a software engineer? I am interested in Dynatrace because observability sits at the intersection of distributed systems, developer experience, and measurable customer impact. I enjoy building reliable software that turns complex runtime behavior into useful decisions. My strengths in backend development, performance analysis, and automation would help improve ingestion, processing, or platform reliability. I also value engineering feedback and ownership. I would contribute by shipping carefully, measuring outcomes, and learning the operational realities behind customer environments. Discuss Dynatrace's observability mission, distributed systems challenges, software quality, customer impact, technical curiosity, collaboration, ownership, and a specific contribution aligned with your strongest engineering experience. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.